Hello, I am Dr. K. K. Misra from our classes. In the series of discussing topics on queuing theory, this is part third. Part first and second have already been uploaded. Here in this, I will be covering today probabilistic queuing model, Poisson exponential single server model, infinite population, and cost analysis. Probabilistic queuing models. There could be three. One, Poisson exponential single server model, infinite population, which will be covered in this video tutorial. And the other two, B and C, Poisson exponential single server model, finite population, and Poisson exponential multiple server model, infinite population, in the next video tutorial. Let us take up, say here, the if the arrival rate of customers are independent with average arrival rate equal to lambda per period of time, then according to the Poisson probability distribution, this is a general one, the probability that n customers will arrive in the system during a given interval of time capital T is normally given by e to the power minus m, m to the power n upon factorial n, where m is equal to lambda t, the arrival rate as already given, and the interval of during the time period in which the customers n number of customers appear or arrive. And the value of E is equal to 2.7183. Mind it, students, you need to have a scientific calculator in order to solve the problems based on queuing theory. As earlier I spoke that I would just covering and discussing here theoretical portion of queuing theory, related formulae and different terms in detail. Then after I will be covering taking up the practical aspects by taking up the practical problems wherein you will literally learn that how to solve the problem. So first, since for the past two video tutorials uploaded earlier and this is the third one, that I am just covering the concepts, methods and procedure in queuing theory. First, let us take a first one, which is the major portion of this video tutorial, that is Poisson exponential single server model, infinite population. This model is based on the following assumptions. Let me tell you that almost every model has got certain assumption. Here, in this case, the first one, the arrivals follow Poisson distribution and with mean arrival rate, say lambda. Second, the service time has exponential distribution. Let the average service rate be mu. Arrivals are from infinite population. The customers are served on a first come first served basis and there is only one single service station. To evaluate the model, we begin with the first equation, whether the service station can handle the customer demand for service. The answer to this lies in the values of mu and lambda. As the conditions had already been discussed in previous video tutorial, if lambda is greater than mu, that is lambda is again the rate of arrival of the customers and mu the service rate at which they are being served, the waiting line would increase without limit and leading to the breakdown of the system ultimately. For a workable system, it is necessary that lambda is less than mu. It is interesting to observe that even if lambda is mu, the system will not work. This can be shown even mathematically. As pointed out earlier, the ratio rho, that is lambda upon mu, is defined as the traffic intensity. This indicates the proportion of time or the probability that the service station is busy. From this, the probability that the system is idle, that is, there are no customers in the system, will be 1 minus rho or 1 minus lambda upon mu, that is P0. We can show that the probability of having exactly one customer in the system, that is P1, so rho into P0. Similarly, this may go on P2 and P3 and all, and then we can have a general term like Pn is equal to rho to the power n 1 minus rho. We can use this result to determine the expected number of customers in the system. So keep this in mind, that this formula is actually important for determining if somebody asks, or in the question it is asked that what could be the expected number of customers in the system. So for that, the formula is rho, that is lambda upon mu to the power n multiplied by 1 minus rho, that is ls. Here this further can be obtained, the expected number of customers ls, that is lambda upon mu minus lambda, or rho upon 1 minus rho. Expected number of customers in the queue shall be equal to the difference between the expected number of customers in the system and the expected number of customers being served at any point in time. Now, since the server is busy or is serving 1 unit lambda mu of the time and is serving 0 unit, that is idle 1 minus lambda upon mu of the time, the expected number being served equals to 1 into lambda upon mu plus 0 into 1 minus lambda upon mu, that is again lambda upon mu. So consequently, expected number of customers in the queue, that is LQ, here that was in the system, here it is Q, mind it, LS, expected number of customers in the system, here it is Q, LQ, that is LS minus lambda upon mu. So finally it comes out to be, that is lambda square upon mu into mu minus lambda, or rho square upon 1 minus rho. It is significant to note that LQ is the average length of all queues including empty queues. The average length of non-empty queues, that is those which contain at least one customer, LQ, is given by the following expression. LQ is equal to 1 upon 1 minus rho or mu upon mu minus lambda. When the average arrival rate of lambda, the average time between arrivals, is 1 upon lambda, thus the mean waiting time in queue, that is WQ, is the product of average time between the arrivals and the average queue length. Symbolically, it is written as WQ is equal to 1 upon lambda into LQ. Substituting the values lambda square upon mu into mu minus lambda or LQ, and then we can simplify it for WQ is equal to lambda upon mu into mu minus lambda, or rho upon mu minus lambda. Similarly, the mean time in the system, that is Ws, that was WQ minded. Now here we are talking about the system. There are two things, queue and system. So we are talking about now system, that is Ws is equal to the product of average time between arrivals and the average number of customers in the system. Thus, this is Ws, that is Ls into 1 upon lambda. Here, putting Ls is equal to lambda upon mu minus lambda in this equation and simplifying, we get Ws is equal to 1 upon mu minus lambda. Stated another way, since the mean service rate is mu, the average expected time for completing the service is 1 upon mu. Therefore, the expected time a customer would spend in the system shall be equal to the expected waiting time in the queue plus the average processing time or servicing time. Thus, Ws is equal to Wq plus 1 upon mu. And finally, if we calculate it, then here you see that it is equal to 1 upon mu minus lambda, which is the same as shown earlier. Finally, the probability that a customer spends more than t units of time in the system, that is Ws t e to the power minus t upon Ws, and the probability that a customer spends more than t units of time in the queue, so that is Wqt rho into e to the power minus t upon Ws. It is significant to note that although the time spent in the system is distributed exponentially and so is the service time, but the difference of the two, that is to say the time spent in the queue, Wqt, is not exponentially distributed. Mind it, these may appear to you theoretically little bit heavy one, but the moment we will be taking up the different questions to solve the examples, through the examples the concept will become more clear to you. Now let us talk about the cost analysis. Queuing theory can be even applied to a variety of operational situations where it is not possible to predict accurately the arrival rate or time of customers and service rate of service facility or facilities. Thus, it is needed to determine the level of service, either the service rate or the number of service facilities, that balances the following two conditions: conflicting costs, cost of offering the service and cost incurred during the delay in offering the service. The first cost is associated with service facilities and their operation. The second represents the cost of customers waiting time. This can well be understood with this particular graph, which is in between level of service on axis X and cost of operation on service Y. Now you see that how total expected cost, the way initially it is high and then it increases. And then the relationships between optimum level, service level, and the cost of operating the service facility per unit of time. This can be, and the cost of customers per unit time can be clearly understood by taking up one practical example. So the complete illustration I would be giving it while I'll take up a practical example specifically on cost analysis so that it becomes more clear. So this was all about this third part of the queuing theory. The rest of the portion, theoretical portion, will be covered in the next video tutorial. For more video tutorials on quantitative techniques, you can, refer to my channel or classes. Thank you very much. Please like, share, and subscribe. Thank you. Have a nice time.